Okay, good evening, everyone. Okay, welcome to our class. All right, so as what I mentioned in the announcement, what we will do first is we will finish up the lecture material on the number systems, and once we are done with that, we can actually go through the tutorial one. Okay, so for the tutorials, all right, once we are done, I will also upload the solutions as well as a video recording of the discussions that we have. Okay, since it's also in the lecture, you can also look at the lecture recording to review the tutorial as well. Okay, so let's get started. All right. Okay, so we basically stopped here last lesson where we were talking about positive and negative values. We talked about the ones complement, twos complement. All right. And we saw how numbers are represented in both positive and negative notation, okay, in the system. Okay, and then we reviewed this particular question, and I think the important thing about this question is the realization that different systems, different compilers or different development tools may interpret some of uh, these numbers a bit differently. All right, so when it comes to integers or float or double, all right, exactly how many bits it represents may vary, okay, depending on the system that you're dealing with. Okay, so that is the important thing to note. All right, so again, this is important for you all, even though you may be developing software at a high level. Okay, you must still be aware of the type of systems your software will run in and how it may deal with data, correct? And is that going to be a factor in your design as well? Okay, so in one's complement, all right, basically all we need to do is we saw that we complement all the bits. In two's complement, we complement and then add one. Okay, so that is what we do. So these are the examples over here. So as you can see, basically what we need to do is we just need to follow the same process as before. That means in terms of, let's say you're doing a ones complement, okay, given this number here, 0101.01, I complement it. So 0 becomes 1, 1 becomes 0, and so on. Okay. And you extend that idea to the fractional part as well. So in this case, 0 becomes 1, 1 becomes 0. Okay, so there is no difference in the approach. In two's complement is the same thing. Okay, so if I look at this number, 0101.01. Okay, when I do the ones complement, so two's complement is ones complement and then you add 1 to it. So here two's complement, one's complement will be first you invert and then you add a 1 to it. You get 11.0101. Okay, so the approach is very much similar. Then you can extend the idea from the integer part to the fractional part as well. Okay, now why is this idea of complements important? All right, because in your processor, when you are doing arithmetic operations, okay, addition and subtraction, multiplication, division, right? These are the four main arithmetic operations. And since uh, addition, okay, is another way of performing subtraction, okay, mathematically. Okay, so if you look at it, x, okay, minus y is the same as saying x plus minus y, correct? Because plus and minus will give you minus, all right? So the key factor is I can perform a subtraction using addition of the negated value. Alright, so mathematically we know this, correct? And this actually helps us because it means that in terms of the processor hardware design, I do not need to have separate hardware blocks to do addition and subtraction. I can just do the negation of a value and still keep the same addition or what you call the adder block. All right, so these are things that you will see later when we start the MIPS processor topic. Okay, so coming back to this, if I were to perform the addition or subtraction on numbers, okay, so let's look at the rules over here. For 2's complement, you perform the addition, ignore the carry, and check for overflow. Okay, so overflow occurs if the carry in and carry out of the most significant bit are different, or the result is opposite sign of A and B. All right, that means in a sense, if the answer doesn't make sense. Okay, so let me show you through example. Okay, what I mean. Okay, so for example, if I take this addition here, minus 8 and plus 7. All right, sorry, this is the range of 2-bit system. Okay, sorry, this is not the addition. The addition is this, 5 plus 6 is 0101 plus 0110. Okay, so these are both positive numbers. Okay, so this is actually the range of a 2's complement system for 4-bit. Okay, so if you look back at our earlier slides, okay, when you say 4 bits, okay, so let me put it here first. So when you say 4-bit, it is basically 2 to the power of 4, which is 16. All right. So rightfully, you have 16 different possible representations, okay, which actually range from 0000 all the way to 1111. Okay. But in a 2's complement system, again 0000 to 1111, but you are splitting the entire range in two, correct? One is positive, the other is negative. So the positive, it goes from 0000 up to 0111, and the negative goes from 1000 up to 1111. Okay. Now, so this range, this positive range, and this is a negative range. Okay, why? Because if you remember our 2's complement system, the most significant bit tells you whether it's positive or negative number. So positive means it is a 0, and negative means it's a 1. Okay, this is the most significant bit. Okay, so maybe I'll just go back to that earlier slide here. Okay, our 2's complement, so you can see what we talked about. Okay, so the range for 2's complement number here is minus 2 to the power n minus 1 to 2 to the power n minus 1 minus 1. Okay, so coming back here, so what you will have is minus 2 to the power of n minus 1 to 2 to the power n minus 1 minus 1. So it will be minus 2 to the power of 3 to 2 to the power of 3 minus 1. So it's minus 8 to 7. Okay, so that is how you can get the range. Okay, that means this 4-bit 2's complement system can represent numbers from minus 8 to 7. Now, if I look at this addition here, 0101 add with 0110, what happens? So when I do this addition, 1 plus 0 is 1, 0 plus 1 is 1, 1 plus 1 is 0, carry 1, and 1 plus 0 is 1. Okay. Now what do you see? You see a number which is 1011. Okay, and when you see this number 1011, the first thing that that should strike your mind is that the most significant bit is a 1, which means, okay, it is actually a negative number, correct? Okay, because in the 2's complement system, the most significant bit will tell you whether it's a positive or negative number. So if the most significant bit is 1, then this represents a negative number. But what is the funny part here? The funny part here is this is actually positive 5 and this is positive 6. I took two positive numbers and I added them together, and we know that mathematically two positive numbers add together, I must get a positive number as the answer, correct? But in this case, I actually getting a negative number as the answer. So the answer doesn't make sense. All right. So this is what I mentioned just now. The answer doesn't make sense because you have two positive numbers added together, but your final result is actually negative based on the most significant bit. So that is what we call a overflow condition. Okay, that's what we call a overflow condition. And for this overflow condition, okay, the moment you see that this is happening, it is an indication that you have a result that is actually out of the range of the number of bits that you have. Okay, so it is not that the answer is actually wrong. All right, the answer is actually correct, but the thing is you do not have enough bits to represent the answer, so it looks wrong. Okay, because 4 bits is not enough to represent the answer, because plus 5 plus 6 is actually plus 11. Okay, and if you look 1011 is actually 11. All right, if you key in your calculator or in your system, it will show is 11. But because your calculator or your laptop computer is operating on a 32-bit system or 64-bit system, all right, it automatically assumes the bits in front are 0. So it interprets it as a 1011. All right, it's operating as a 32-bit sign system or a 64-bit sign system. But in our case, we are limiting it to just a 4-bit system. So the answer cannot fit into 4 bits. So if I were to use a 5-bit system or a 6-bit system, then no problem. Okay, then the answer would have been interpreted correctly. Okay, so similarly over here, I have two negative numbers add together, and the answer I get is actually a positive number. All right, so whenever you have situations like this where positive numbers add together become negative, or negative numbers add together become positive, then you know that something has gone wrong. Okay, now let's look at some more examples here, and then you will see how this works. Okay, now for positive numbers, I don't think any of us will have an issue with representing them. Okay, if you don't quite remember how, okay, you can always use your calculator. Okay, so I mean, we saw one of the earlier slides, you can do the continual division by 2 to represent or to convert a decimal to binary, but that is not necessary. You can just use your calculator. So for example, over here, if I were to key in decimal 3, okay, you can see the answer binary is 0011. Okay, similarly, if I were to key in 7, you will say 0111. Okay, how about negative numbers? Okay, so in this case, negative numbers, what I can do is I can put in 2 and I can click on the plus minus sign over here. So when I click on that, okay, what happens is it does the 2's complement for me, but it will use the full number of bits that the system is using. Okay, so if you're using a 64-bit system, it will represent the answer in 64 bits. Okay, so it all depends on what kind of a system your calculator is running on. Okay, so in this case, okay, here I have a 32-bit system. All right, so I'm representing, okay, this is 64-bit system. All right, so I'm representing my answer in 64 bits. Okay, now the thing that you need to remember is, since I am only representing this addition in 4 bits in the question, I only need to focus on the lower 4 bits, which is 1110. Okay, if you want to go through the manual way of representing or converting it, okay, how you can do it is performing the 2's complement on your own. Okay, so how do you perform the 2's complement on your own? Okay, so let's take this example, 2. Okay, so what you first need to do is you need to take 2 and represent it in its original form. So instead of looking at the minus, you imagine that 2 is positive. So positive 2 is represented as 0010. Okay, so if I want -2, what I need to do? I need to do the 2's complement. So -2 means I need to first flip the bits 1 1 0 1 and then I add a 1 to it. Okay, so let me do it here. 1 1 0 1, add a 1 to it. So I'll get 0, carry 1 1 1 1. So this is -2. Okay, so anytime I want to take any number and find the negative representation of it in 2's complement, I just take the positive uh, version of the number in binary and then do the 2's complement. That will give me the negative representation. Okay, so if I look at these examples here, so I'll not go through everything, but what you can see here is, okay, so here we are checking which of them are overflow. Now the first one, as you can see, this is a positive number, the answer is positive. All right, so if positive and with positive, the answer is still positive, then there is no issue, there is no overflow. Okay, in 2's complement, whenever you have a final carry over, you can discard the carry. Okay, so in this case, there's a carry over from here to here, but you do not need to worry about the carry, you can discard it. Okay, so what you have here is a negative number, add with another negative number, because 1 and 1, and the final answer is still negative. Okay, so there's no issue. In this case, again, positive and negative. So whenever you have positive and negative, all right, there should be no issue in having an answer that is within the range. Okay, but you can always check with the second condition, which says that the carry in and carry out, okay, must fulfill the condition. Okay, so let's look at that second condition over here. Carry in and carry out of the MSB are different. That is also an indication of overflow. So let me show you how to check for this. Now if I do this addition over here, 0 plus 1 is 1. Okay, 1 plus 0 is 1. 1 plus 1 is 0, carry 1. Okay, 1 plus 1 is 0, carry 1. Okay, so if I look at this most significant bit, what happened? 1 plus 1 is 0, carry 1. So the carry in, okay, the carry in to the most significant bit is a 1. Then 1 plus 1 is 0, carry 1. And the carry out of the most significant bit is also 1. Okay, so the carry in was 1. Okay, so we're only focusing on the most significant bit. The carry in is 1 and the carry out is also 1. So since they are both the same, you can also say that there is no overflow in this case. All right. So again over here, positive and negative, no overflow. Okay, so these last two examples, we say there's overflow. Okay, so why is there overflow? Because you can see that in both these cases, okay, the answer here, okay, or the two numbers here are negative because most significant bit is 1, but the final answer is positive. Okay, so like I said, the answer doesn't make sense because you have two negative numbers adding together and the answer is positive, so it doesn't make sense. So we say it's an overflow condition. Similarly, in this example, positive and with positive, you end up with a negative number. So again, it doesn't make sense. So we say it's a overflow condition. Okay, so this is what I mentioned just now, where you do the 2's complement subtraction by actually performing addition, okay, of the complement. Okay, so whenever you do deal with 2's complement system, okay, when you get your final answer, okay, when you get your final answer like this, okay, you cannot directly interpret this by putting it in a calculator. Okay, why? Because this is actually a negative number, correct? The most significant bit is 1. When the most significant bit is 0, there is no difference. Okay, for example, if I look at this 0 1 0 1, 0 1 1 1, okay, so in this case, but this is a overflow condition, so let's not talk about this part here. But if I look at this condition here, okay, 0 1 0 1 is 5. You key in a calculator, you get 5. Okay, 1 1 0 1, if you key in a calculator, what you get is 13. Okay, because you will interpret it as a positive number. But we know that this is actually a negative number because the most significant bit here is a 1. Okay, so when the most significant bit is a 1, okay, what you need to do is to get the correct interpretation of this number, you need to do 2's complement one more time. All right, so if when I do an addition and the final answer has the most significant bit as 1, what I need to do, I need to do 2's complement one more time. So 1101, I do 2's complement one more time, so I'll get 0 0 1 0. That is the flip, and then I add 1. So I'll get 1 1 0 0, and this is 3. Correct? 0 0 1 1 is 3, but because the most significant bit is a 1, that tells me is actually a negative 3. Okay, so this is the part you must be careful. When your answer has the most significant bit as 1, okay, you cannot directly use a calculator to tell you the value. You must do 2's complement one more time to get the value, and then put a minus sign in front of it. Okay, so for 1's complement, it is similar. The only difference is if there's a carry out of the MSB, you add 1 to the result. In the previous case, okay, we saw that whenever there is a carry out like this, whenever there's a carry out over here, we just ignore it. Okay, for 2's complement, when there's a carry out, we ignore the carry out. Okay, we don't factor that in the answer. But in 1's complement, if there's a carry out, we need to take that carry and add 1 back to the result. Okay, so let's see what we mean. So the example here is what is shown. That means the same representation, -2 and -5. Okay, so how you get -2? So this is only 1's complement, correct? So you just flip. So 2 is positive 2 is represented as 0 0 1 0. So negative 2 is 1 1 0 1. Similarly, positive 5 is 0 1 0 1. So negative 5 is 1 0 1 0. Okay, so this is 1's complement. So in 1's complement, after I do the addition, okay, I get carry out. So this carry out, I need to add back to the LSB and get the final answer. Okay, so that is the only difference between the 1's complement and 2's complement addition. Okay, so this excess representation, I will not talk too much about it. It is just another form of representation, and the whole idea is you move your sort of 0 point or starting point to somewhere else in the full range of numbers. Okay, so if I look at this example, I have 3-bit numbers. So 3-bit numbers basically say is 0 0 0 all the way to 1 1 1. Okay, so this is the full range. Okay, so normally if we count, we'll say 0 0 0 is 0, 0 0 1 is 1, and so on. But that is how we normally count. Okay, in excess representation, basically what we can do is we can say that if I say I use excess 4, then 4, which is this 100, is now the new 0. Okay, it's now the new 0. Okay, so from the new 0, okay, you can count forward or backward. Okay, so this is just another way of representing data, okay, which is used in some cases, but I will not go through too much about this. Okay, so the last part of this chapter here is on this topic called real numbers. Okay, so until now, we have been looking at representing positive and negative numbers using the 2's complement system, and that is also the system used in our day-to-day computers that we deal with. Okay, but again, those are for whole numbers, correct so far. But how about real numbers? Okay, in real numbers, we're talking about systems or numbers with many decimal points, or in some cases very large or very small. Okay, So in this kind of situations, how do we use bits to represent this information? So there are a few different formats. Okay, one is what we call the fixed point representation, which is something we saw earlier when we were talking about the two's complement sort of format. In fixed point representation, what we can do is we can take any number of bits and we can say that a certain number of bits is reserved for the integer part and a certain number of bits is reserved for the fractional part. Okay, so if I were to take this 8-bit system, I can say that, okay, 6 bits are for the integer part, okay, over here, and 2 bits are for the fractional part. Okay, so that can work very easily, okay, as what we saw earlier. And you can use one's complement, you can use two's complement and still represent all the numbers. Okay, but of course the issue is you're having a fixed point representation. So if you need more resolution in terms of your decimal places, it will be a challenge. All right. Okay, so it is easy to implement, okay, but it is not a good way to really represent the real world numbers that we deal with. So the other, so of course, the other one is the alternative, okay, where we need to look at numbers like this, correct, where we have very, very large positive numbers, very small positive numbers, very small negative numbers, and so on. Okay, so when I have this kind of very extreme numbers, I still need to be able to represent them in my system, correct? Because when you write a code, you may have to deal with this kind of numbers. So that is where there's another well-established and widely used format called the IEEE 754 floating point format. Okay, and in this format, basically what we have done is they have taken the total number of bits and broken it up into 3 parts, which will be used uh, to represent numbers that actually have this wide scale. Okay, and there are 2 versions to it. One is the 32-bit version and the other one is 64-bit version. Okay, single or double precision. We will be only focusing on the single precision format, okay, for this module, just to understand how this works. Okay, so if you look at this, there are basically 3 parts to it. One is the sign bit, that is a single bit. Then there's a 8-bit exponent and 23-bit Mantissa. Okay, how do you get this representation? Okay, it is a fairly easy process. The first is the sign bit. For the sign bit, if it is 0, it is positive, 1 is negative. So very similar to what we've been seeing for the complement systems. The next is the normalization of the data. Okay, so given the binary representation, you normalize the data. So normalize the data means you move the decimal point, okay, until you have a leading 1 bit. Okay, that means the first bit must become a 1. All right, and only a 1. So if I have 110.1, okay, when I represent my data in binary form, I move my decimal point until I only have a single 1. All right, and since I moved back by 2 places, I multiply by 2 to the power of 2. Okay, now once I do that, okay, basically I have 2 parts already. This 101 goes to the Mantissa, and this will be used to derive my exponent. Okay, so let's look at an example here. Okay, and then you can see how it works. So firstly is negative 6.5. How do I represent this? So negative 6.5, again, the first step is you don't need to worry about the negative part. Okay, you just focus on 6.5. So 6 is this 110, and after the decimal point, if you recall, it is 0.5, 0.25, 0.125, and so on. Okay, because after the decimal point, okay, each bit is 2 to the power of -1, -2, and so on. So this is 2 to the power of -1, -2, -3, and so on. This is after the decimal point. Before a decimal points, it is 2 to the power of 0, 2 to the power of 1, and so on. Okay, so after the decimal point, this is 0.5, 0.5. Now, so the first step that we saw was we need to normalize the data, so the decimal point has to shift. So this decimal point has to shift until I only have a single one in front. Okay, so since I shifted by 2 places to the left, I will multiply by 2 to the power of 2. Okay, so if I shifted by 3 places, it will be 2 to the power of 3 and so on. Okay, so that is the normalization. Okay, once I normalize, the next few steps are very easy. Since the sign is negative, the sign bit here is a 1. All right. Next is the exponent. So the exponent is basically uh, calculated by taking 127 at the power, okay, which is this 2. So 127 plus 2 is 129, and 129, if you key in a calculator, you will get this 8-bit representation here. So that entire value comes inside here. Okay, so this entire value comes inside here. And finally is the Mantissa. And what is the Mantissa? Is basically whatever is remaining after the decimal point when you have done the normalization. Okay, so what you have is 101. If you remember just now, we said this is 23 bits, correct? But you only have 3 bits. So the remaining bits will all be 0. Okay, so this 101 is actually from here. Okay, and since you only have 3 bits after the decimal point, the rest of the bits over here will automatically be 0. Okay, so this entire representation is actually in this entire this full 32-bit string over here. In to make it simpler to read and understand, we will usually represent such long bit streams in hexadecimal form. So in hexadecimal form, basically you group it into groups of 4. Okay, so this is one group, one group, one group, and so on. So this will be C, this will be 0, this will be D, and the rest is all 0. Okay, so that is how you get the final answer here in hexadecimal format. Okay, so that is basically the last part over here on the IEEE 754 floating point representation. So this format is actually very powerful because you can represent uh, the kind of number that we saw earlier, very, very large numbers or very small numbers, still very effectively and very accurately with this particular system. All right, so it is still very widely used in many processors out there. Okay, so okay, these videos and all you can have a look, okay, to just reinforce this concept. Okay, so that brings us to the end of this set of slides here. Okay, so what we can do now is we can actually move over to our first tutorial, tutorial 1. Okay, and then review these concepts. Okay, if you have looked at it, it is okay. If not, we will go through the questions now. Okay, and we will look at how to solve them. Okay, so please take out your tutorial question. So in this tutorial 1, okay, is basically to recap what we have done in terms of the number systems and C programming. Okay, so let's get started here. So in the first question here, we are asked to solve this 1's complement. Okay, so this explanation all here, we don't need to worry so much. Okay, the concept that we are trying to introduce you to is this thing called the sign extension. Okay, so what is sign extension? Okay, sign extension is basically a way of making sure that when you add or subtract two numbers, we take into account that we both have the same number of bits to represent them. Okay, so let's look at this, okay, and understand how it works. Okay, okay, so let's look at it over here. So we are now given these two binary representations of a number, okay, and you are asked to solve for this. All right, so the first thing is, now if I were to think about it, all right, sign extension is something that you already have been doing in your normal decimal places, correct? Okay, so if, for example, if I give you 95 minus 201, okay, you will automatically know that in front here is actually a zero, okay, but you just don't write the zero there, right? But you know that actually it's a zero in front. All right, so this same thinking, the same concept is basically what we're going to be applying over here. Now, the first step is to understand that we are going to first make sure that they are both having the same number of digits in terms of representation. Okay, so let's write out the number. So I have 0101.11. Okay, subtract um, 010.0101. Okay, so what do you see? So firstly, the alignment must be based on the decimal point, correct? Then you can easily see where the extension needs to be done. So there's two parts to this extension. So for the first number, we need to extend the decimal portion. So I put two zeros here. And for the second number, we extend the integer part. So I put one more number, 0 here. Okay, so in terms of sign extension, that is what you need to do. Okay, we need to make sure that the sign is extended, okay, to make sure that the numbers have the same number of bits both in the integer part and fractional part. Now, so that's the first step. Okay, now the second step is we see that we are supposed to do a subtraction. Okay, but from what we have learned, subtraction is nothing more than the addition of the complement. Okay, the addition of the complement. And in this question, okay, we are asked to perform the ones complement. Okay, we are asked to do the ones complement to solve this. Okay, so let's uh, look at how to do the next step. So the next step is we perform the ones complement, okay, of this particular number. So I will get 1101.1010. Okay, so it is now this number subtracting this number, right? But sorry, this number's adding to this number because it is now the addition of the complement, right? The addition of the complement. So let me write these two numbers together now. 0101.1100. This is the first number, and this is the second number, 1101.1010. And now we are going to do the addition. Okay, so again, why we are doing the addition? Because the addition of the complement is the same as the subtraction. Okay, the addition of the complement is the same as the subtraction. So since we already do the complement, we can now do the addition. So let's get the result for the addition. So 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 0, carry 1, 1 plus 1 plus 1 is 1, carry 1, so this is 1, 1 plus 1 is 0, carry 1, and then 1 plus 1 is 0, carry 1. Okay, so since this is one's complement, okay, whenever you have a carry over, you need to add that back to the end. Okay, so the final answer here would be 1 here, 1 1 0 dot 1 1 0 0. Okay, 0 0 1 1 dot 0 1 1 1. Okay, so that is the final answer over here. Now, how do we know for sure that this is the correct answer? You can always convert back to your decimal values, correct, and check what is happening. Okay, so let's do that, okay, and confirm that the answer is correct. So 0011, this integer part. Okay, so for this integer part 0011, this is 3. Okay, now for this fractional part. Okay, so if you remember just now, we said this is the first decimal point is to the power of -1. So this is to the power of -2. This is 0. So 0.5, 0.25, 0.125. Okay, this is 0.0625. Okay, so you have to remember that they are the to the powers. Okay, so this is to the power of -2, to the power of -3, to the power of -4. Okay, now if I were to add up all of this, okay, 0.25, 0.125, 0.0625, I'll get 0.4375. So the answer here is 3.4375. So this is the answer that I get by converting this final answer from binary to decimal. Okay, let's check back with the original two numbers. So this number here 0101, this is 5, and this is 0.5, 0.25 is 0.75, so it's 5.75. Okay, this number here is 2, and this is 0101, this is 0.25, and this is 0.0625, so this is 2.3125. Okay, so if you take 5.75, subtract 2.3125, you will get 3.4375. Okay, so you can see that they are the same. Okay, so you can relate now, okay, that what we have done, okay, with the sign extension and with the ones complement is indeed correct. Okay, because when you go back to the decimal representation and you do the calculation, you get the same answer. Okay, so that is part A, question 1, part A. Okay, so this is basically what we saw just now and last week as well, the ones complement with integer part and fractional part. All right, and we are just doing the subtraction. Okay, but the important concept that we are showing you here is to make sure that the when you do this kind of operations, the decimal point must be aligned, and you do the proper sort of padding or extension at the decimal side as well as the integer side. Okay, now let's look at part B over here. Okay, part B is also another similar type of question. So let's see what we have here. So let's do the same thing. Let's write out the numbers first. 0, 1, 0, 1, 1, 1 dot 101, subtract 0, 1. Okay, wait. Let me okay, so let me go from the decimal point so it's easier to keep track. Okay, and make sure everything is aligned. So 0, 1, 0, 1, 1, 1, 0. Okay, so in this way it's a bit easier for me to see that I need to do a padding. Okay, so I need to do a padding here and a padding here. All right, so that will make sure that both of them now have the same number of bits, okay, in terms of representation. Now, so that is the first step. And in the second step, basically what we saw is, instead of doing a subtraction, we will do the addition of the complement. So we now need to do a complement of the second number over here. So I'll get 1, 0, 0, 0, 1, 0, 1 dot 0, 0, 1. Okay, so that is the complement of this. So right now we know that we need to focus on this number, okay, and we perform an addition with this number, correct? Because the addition of the negated number is actually the same as doing the subtraction. Okay, so let me write both the numbers at the side again. So 0, 0, 1, 0, 1, 1, 1 dot 1, 0, 1, and this is the addition of addition to 1, 0, 0, 0, 1, 0, 1 dot 0, 0, 1. Okay, so let's do this addition now. So I get 1 plus 1, 0, carry 1, 1, 1, 1 plus 1, 0, carry 1, 1 plus 1, 0, carry 1, 1 plus 1 plus 1 is 1, carry 1, this is 1, 1, 0, and 1. Okay, let's look at this answer now. Let's look at this answer and see what we get. If I were to look at this answer, okay, and I were to directly interpret it, okay, what will I get? Okay, so 1, 0, 1, 1, 1, 0, 0. Okay, if you use your calculator, okay, let me key it over here. So 1, 0, 1, 1, 1, 0, 0 is actually 92. Okay, in binary, that string here is 92. So this would be 92. Okay, and this is 0.5 and 0.25, so it's 0.75, so 92.75. Okay, so let's look back at these two numbers here. Okay, 0, 1, 0, 1, 1, 1. Okay, if you key this in your calculator, okay, you will get 23 point, so 101, you get 625. Okay, and this number here will be 58.75. So the answer you should be getting here should be minus, okay, 35.125. Okay, but if you interpret this answer, okay, with its current values, you get 92.75. All right, and anybody can tell me why the answers are not the same?
You have to move the 1.
Sorry,
I think you have to move the 1.
move the one, which one? This one, is it?
Yeah, because the first one is 1. The first digit is 1
Okay,
of
so
the answer lah.
correct. So what must I do? So the first digit is 1. Yeah, so it's correct. So what you need to do, you need to do the ones complement. Okay, so as what I mentioned just now, as long as in your final answer, your most significant bit is a 1, you cannot directly interpret it. Okay, that means it is actually telling you it is a negative number. So to get the actual value, you still need to do the complement one more time. You need to complement one more time. Okay, so what you need to do here is take this number 1011100.110, and you need to do the ones complement again. So I'll get 0100011.001. Okay, now if you take this and you key in your calculator, then you will get, okay, that this is 35 and this is 0.125, and then you go back to see that this, since the most significant bit was a 1, then I put a minus in front here. Okay, and that will be the final answer. All right, and then you can see that it is the same. All right, so whenever your final answer is having a more significant bit of 1, okay, you must do the complement one more time, okay, and then you get the value, and after you get the value, you put the minus sign in front. Okay, so that is how you interpret or solve this question here. Okay, so that is basically for question 1. Okay, let me go on to question 2 on the IEEE format. Okay, so for this IEEE format, we just saw it, all right. So you can just take it as a refresher, okay, on how to do it. Okay, so for exams, yes, you are allowed your calculator, so no issues with that. Okay, so let me come to this question here. So this is like what I mentioned is now a small negative number, and you want to represent this in the IEEE format. Okay, so the first step is this is in decimal form, negative 0.078125. This is actually decimal, that means it's still a base 10. Okay, I need to convert this to a number in base 2. All right, so to convert a decimal to base 2, if it is integer part, no problem. Okay, your calculator, you key in, it will give you the answer straight away. Fractional parts have a challenge, correct? Maybe some of your calculators might be able to do it, but most calculators may not be able to do it. Okay, so we still have to go back to the more of a pen and paper approach, which is to do the repeated multiplication by 2. Okay, the integer part you do the division by 2, the fractional part you do the multiplication by 2. Okay, so let me go through the steps over here. Okay, so you don't need to worry about the negative sign, okay, when you're doing the conversion from decimal to binary. You just focus on the actual value itself. Okay, so 0.078 125. I need to first multiply by 2. I'll get 0.15625. Okay, so in terms of the binary, since if the value in front of the decimal is 0, this will be a 0. Okay, and then I repeat again, 0.15625 times 2. I'll get 0.33125. Okay, so these steps are the same steps in your lecture notes. Okay, so I just need to keep on doing it until I hit 1. Okay, so 0.625 and then 0 times 2, I will get 1.25. Okay, so I get a 1, and so once you get a 1, you discard that 1, so 0.25 times 2, get 0.5, and you get a 0 here, and this will be the last one, 0.5 times 2, you get 1.0. Okay, so the 1 comes here. Okay, so now you can stop. Okay, and this will be your MSB, most significant bit, and this will be your least significant bit. Okay, in terms of from the decimal point. Okay, so the answer here, okay, in terms of binary is 0.000101. Okay, so of course the negative is still there. Okay, so this is the first step. You convert from decimal to binary. Okay, decimal to binary. After you convert from decimal to binary, then you can go ahead to perform the steps for the IEEE 754 conversion. Okay, so for the IEEE 754 conversion, you first normalize. Correct? So normalize means you move the decimal point until you get the first one. Okay, so what you get now is 1.01, okay, negative, multiplied by 2 to the power of, so since I move 4 spaces is negative 4. Okay, whenever you move to the right, okay, it is negative. You move to the left, that is positive. Okay, uh, so once you get this, it is now easy to translate it to your 754 format, because this negative sign tells you the sign bit. Correct, so the sign bit will be a 1. Alright, that's the first thing. This minus 4, basically what you need to do is you say 1, 2, 7. Okay, add with this, so add with minus 4 will give me your exponent. So this is 1, 2, 3. Okay, 1, 2, 3 in binary. Okay, you can key in your calculator. 1, 1, 0, 1, 1. So that is 1, 2, 3 in binary. And whatever is after the decimal point over here, this will be the Mantissa. All right, so let me put it all together over here. So, okay, so you have the sign bit, you have the 8-bit, and then you have the Mantissa. Okay, so this is the sign bit, which is a 1. All right, and then you have your exponent, which is this part over here, 0, 1, 1, 1, 1, 0, 1, 1, and then finally you have your Mantissa, and the Mantissa is whatever is after the decimal point. Okay, so in this case you only have 0, 1, so the rest of it will be zeros. Okay, so that is basically the final answer. Okay, but as we saw in the lecture slides, to put 32 bits and then check whether it's correct is a very tedious task. Okay, so usually what we will do is we will group them or we convert them to hexadecimal format. Okay, so let me rewrite this string over here. So you have 1, 0, 1, 1, 1, 1, 0, 1, 1, 0, 1, and then the rest are all zeros. Okay, so we need to group them into bits of 4. So 1011 is one group, 1101 is one group, 1010 is one group, and the rest are all zeros. Okay, so when I convert this, this will be B, this will be D, this will be A, and everything else will be 0. Correct, so the final answer, okay, you can write it as B, D, A, 0, 0, 0, 0, 0, base 16. Okay, so that is basically how you perform this conversion, okay, in the 754 IEEE format. Okay, so I know we just saw this, all right, so if you still not sure any of the steps, you can just go through again, okay, when you're free, and then you see that it's not so difficult, all right, it's just a procedural thing. As long as you know how to convert from decimal to binary, the rest is just going through the steps to understand the sign bit, the exponent, and the Mantissa. Okay, that's all. Okay, so okay, question 3 is on C programming. Okay, so for the C programming part, I think most of you should not have any issues with it. All right, in terms of reading array. Okay, in terms of reading array, I'll just quickly go through the solution. Okay, so to read array, okay, so you have you pass in an array and you pass in the count. All right, so you will usually have so variable, I, input, and so on. Okay, and then you have a printf to ask the user to key in something, and we want maximum 10. And if you look at the handout, any negative number will also stop it. Correct. Okay, so we initialize I to 0 and we take the first scanf. Okay, so in the first scanf, we capture it into our variable input. And after that, what we do, we want to make sure that we keep on repeating, but there are two conditions, correct? So we can use a while loop with two conditions. So the two conditions are if while the input is greater than 0, because any negative number you want to end the loop, and I is less than 10. Okay, because you want to take maximum of 10 numbers. Okay, so that is basically the conditional checking to make sure to decide whether to repeat or not to repeat the loop. Okay, and once I capture the input from the user, I can pass it over to my array. I can do an increment of my count I, and I can get the next input from the user. Okay, and then I can return I when I'm done. Okay, so that is a very simple code. Okay, I think for most of you shouldn't be any issue to read in an array of numbers. Okay, the main thing is we just want to revise the basic concepts of input output loops, all right, and conditional checking. Okay, the next one is to reverse the array. Okay, so to reverse the array, you are asked to provide two possible solutions. One is the iterative version and the other is the recursive version. Okay, so let's look at the iterative version first. So the iterative version, so void, okay, so reverse array. Okay, so that is the function. So what I can do is I can create a pointer. So integer left equals to 0, right is equals to size minus 1, and do a temp. Okay, and while left is less than right, I do a swap. Okay, swap algorithm, I think all of you know how to do. So I put into a temporary storage first. Okay, array left is equals to array right, and then array right equals to temp. Okay, and then after I do that, I need to increment my pointers or index, sorry, left plus plus and right minus minus. Then I repeat the loop. Okay, so technically what I'm doing here is I'm taking this entire array and I'm creating two index, the left index here and the right index here. Okay, and what I'm doing is while my left is smaller than my right, I swap. Okay, so the very first time I'll swap this and this. Okay, after I swap, what happens? I will increment my left and decrement my right. Okay, that means my left will now point to the next index over here, and my right will also point to the previous index over here, and so on. Okay, so that is one way of doing this reverse sort of function in an iterative form. There is also the recursive form that you're asked to look at. Okay, how do you do the recursive form? So to do the recursive form, what you can do is you can have a sort of a proxy to take in the function and then call the recursive function. So I can call it maybe recursive to integer array. Okay, and then I call this function recursive reverse. Okay, call pass in the array 0 and size minus 1, and inside this recursive array sorry, this is array, and this will be left and right. Okay, so what I will do is I'll actually do the same thing. I'll create a temporary variable, and then I will say while left is smaller than right. Okay, I will do the swap. Okay, so I'll do the swap as earlier on, but after I do the swap, what will I do? I will call back my same recursive function. Okay, and when I call back, okay, I'll call back my array with left plus 1 and right minus 1. Okay, so what is happening here? It is actually a similar thing as just now. Okay, but what is happening is the very first time I call this function, I pass in the whole array, and my left is pointing here, all right, and my right is pointing here. Okay, but after I do the swap, when I call myself the next time recursively, what is happening? I'm calling in the same array, I'm passing in the same array, but my left has been shifted by 1 to the right, and my right has been decremented by 1 to the left. Okay, that means in the next recursive function, what the function sees is the function only sees this. Okay, with the left pointing here, okay, and the right pointing here. Okay, so I'm still passing in the whole array, but now my index has shifted. All right, so the recursive function sees a smaller array, and again until the condition is no longer fulfilled. Okay, so that is basically two different ways of writing the code to solve this question. Okay, again, you may have other ideas or other implementations, which are fine. All right, so this is just to give you the idea of how to go about solving this. Okay, so let me go on to this last question here. Okay, so for this last question, it is a review on pointers. Okay, pointers we didn't cover much in the actual slides, but I believe you should have some exposure to it. All right, if not, you can just take it here as a form of revision on how it works. Okay, so the first thing is here we have a few variables. Some are normal variables, some are pointer variables. Pointers are one of the most powerful tools in C. Okay, because you can use it to point directly to hardware, which gives it a lot of power. Because in terms of mapping code to directly talk to hardware, that is one of C's powerful strengths. Okay, so here you have a variable a equals to 3. So let me draw that here. So I have a, and I have a value of 3 inside it. Okay, and then I create so b is a pointer, and b is assigned the address of a. So b is a pointer, and it's assigned the address of a. That means what is happening is b is going to point to a. Okay, so that is the first line over here. In the second line here, asterisk b is equals to 5. Asterisk b means whatever b is pointing to. So b is pointing to a. So whatever memory location that b is pointing to, put a value of 5 inside that memory location. So here I will change it to 5. Okay. In the next step, I say c is equals to asterisk b multiplied by 3. Okay, so c is another variable. Okay, so c is another variable here. And what is inside c? C is whatever b is pointing to, asterisk b is whatever b is pointing to, the value multiplied by 3. So the value that b is pointing to is 5, and I multiply by 3, so I'll get 15, and I put that 15 inside here. Okay. In the next line, I say D is equals to D. So what is D? D is also a pointer. And what is inside B? B is having the address of A. So I take the address of A and I put it inside the variable D. So that means that D is also now pointing to A. Okay, D is also pointing to A. In the next line, I say E is equals to asterisk B plus C. So whatever B is pointing to, the value, add with C. So what is B pointing to? B is pointing to A, which has a value of 5. Okay, and I add with C, which is 15, so I get 20, and I put it inside another variable called E. So E is going to have a value of 20. Okay. In my next line, I say asterisk D is equals to C plus E. So C plus E. So 15 plus 20 is 35, and I put it into wherever D is pointing to, and D is pointing to A. Okay, so I'm going to remove this and overwrite it with a value of 35. Okay, then I have one more pointer here F, which is now assigned the value address of A. Okay, so address of E. So address of E is inside pointer F. That means F is now pointing to E. Okay, F is pointing to E, and I say that in this line, I say A is equals to asterisk F plus asterisk B. So variable A is going to take the value of whatever F is pointing to, add with whatever B is pointing to. Okay, so what is F pointing to? F is pointing to E, which is 20. So this is 20 plus whatever B is pointing to, 35. So 20 plus 35 is 55, and put it back inside A. So inside A, I will get 55. Okay, and in the last step over here, I take asterisk F equals to asterisk D minus asterisk B. That means whatever D is pointing to, subtract whatever B is pointing to, and put it into whatever F is pointing to. So both D and B are both pointing to A. Correct? That means they both are pointing to the same value. So 55 minus 55, I'll get 0. And I put it into what? To the place where F is pointing to. So F is pointing to E. So this will now become 0. Okay, so that is basically what is happening in this entire code. All right, so if you have forgotten, okay, a pointers, you can just go and do a quick revision. Okay, when you create a pointer, okay, you are creating the ability for this pointer variable to point to anywhere in memory. Okay, for it to point to anywhere in memory, you must first assign it to the address of the variable. Okay, so if I want P to point to A, I say P equals to M% A. If I want point to C, P equals to M% C. Okay, and wherever I'm pointing to, I can reference that data by using the pointer notation, the asterisk in front of the pointer variable name. Okay, so that is basically how pointers work, and this question is just to revise those concepts. Okay, so I think it's just nice. All right, we can take a break now. Now it's about 7:50. Okay, so I think we can take about 15 minutes break. Okay, so about 8:05, 8:10, I will see you back here. All right. So don't worry if any questions you still have about the tutorial, you can still let me know later on. As I mentioned, I have separate videos for the tutorial, and you can view that, or you can also view the recording of this session after I upload it, okay, to revise and go through what we have discussed. Okay, so additional questions for practice. Okay, I can give you all right, some on number conversion and some on programming as well, just to make sure that you have some good baseline, okay, to start off the remaining topics. Okay, so that one I will prepare and I will upload by the weekend. All right, or probably by I think by Thursday or Friday I should be able to upload. Okay, then you can use that to practice. Okay, so we can go for a break now. And about 8, I think about 8:10, I'll see you back here, and then we will start on our next topic on the MIPS. Okay, so yeah, so I'll see you back here at 8:10. Okay, thank you. Okay, so welcome back. Let's get started. Okay, with our next topic on MIPS. Okay, so let me share the screen. Okay, so this topic on MIPS is quite a big topic. Okay, a few lecture slides cover MIPS. Okay, so we're going to talk about understanding the architecture, okay, how it does basic operations, the control part, the data part, and things like that. Okay, so for the next few weeks, we will be covering in depth into MIPS, also assembly language programming. Okay, how a C code translates to assembly language code and how the assembly language code eventually gets executed by the processor. Okay, so we're going to go into a lot of aspects of low-level architecture. Okay, from a processor perspective. And usually these few slides, the biggest, I think, challenge for many students is if you get uh, a bit lost somewhere along the way, and if you don't close that gap, you will find subsequent classes even more challenging to understand and keep up. Okay, because everything builds up. Okay, everything is interlinked. Okay, so you need to sort of make sure that you are keeping up with the material. Okay, so that when we go from one set of notes to the next set of notes, you are actually able to follow through. Okay, if you get lost in the first few slides on the MIPS assembly language, and then subsequently you'll find it very tough to catch up. Okay, so that is something that you need to do. Okay, everything is interconnected. Okay, so you need to make sure that you keep up with the material as we go along. All right, if not, it will be quite a challenge for you to understand what is happening. All right, and probably when you're just towards the end or when you're doing the assignment, then you have to go back and start all over again to go back and start and see how the whole thing builds up. Okay, so that is something that you need to do to make sure that you understand these next few set of slides well. Okay, so let's get started with the MIPS. So we're going to go through a lot of things: the instruction set architecture, the assembly language, okay, how registers are defined in the processor, okay, and how many of the arithmetic and logical operations can be written in MIPS assembly language. Okay, so let's have a recap first. So we saw that we can write a program in high level C, for example. If you take this simple arithmetic operation A plus B, okay, what we need to do, what happens is when you click on the compile button, all right, when you click on the compile button, the compiler translates your high level language into what we call assembly language. Okay, this assembly language is very specific to the hardware you're dealing with. Okay, in the past, in the 70s, 80s, and so on, assembly language was predominant. Okay, even up to the 90s, many schools were still teaching assembly language in a very detailed fashion because the industry was still using assembly language. Okay, but the main reason or the main drawback with assembly language is when your hardware changes, okay, to a different architecture, you will need to rewrite everything, okay, because it is not portable. Okay, unless if you say it's within the same family, then maybe some aspects may be portable, but in many cases, like for example, if you transition from processor, like I say Intel, okay, to Motorola, okay, it is not portable. Okay, it's a totally different set of assembly language instructions. But within Intel, okay, you change from one processor to another processor, some aspects may still be uh, easy to bring across. Okay, so it's very specific to hardware. Okay, of course, right now the compiler does this for us, so it is a lot more easier to handle. And finally, the assembler translates it to machine language instructions. Again, these are very specific to the processor that is going to execute your code. Okay, so when you in this module, you're going to learn about MIPS processor. So there is a specific set of instructions that the MIPS processor recognizes and deals with it in a particular fashion. If you were to study ARM processor, then that processor has its own architecture and the way in which instructions are written and decoded and executed. Because every processor has its own sort of architecture to deal with instructions at the machine level. So instruction set architecture, as what we saw, is basically the ability to interface hardware and very low level software. Okay, so you're going to be using this instruction set architecture, all right, as a bridge, okay, between these two domains. Okay, and this instruction set architecture includes everything we need to know to make the machine code working. All right, and it allows us to perform the necessary functions, okay, based on the hardware that is given to us. Okay, and like what I mentioned, you have different types of architectures that can run similar software. Okay, so if you take Intel processors, okay, you have 80, 83, 86, then you went on to Pentium and so on. Similarly, AMD has its own set of architectures and so on, and ARM has its own versions. All right, but within them, they may be able to run similar type of software, but to transition from one processor to another processor is not possible at the assembly language. Okay, but at the higher level language, it is a lot easier, correct? Because it's just a matter of making sure the compiler is able to do this translation for us. Okay, so the machine code is the ultimate ones and zeros that your computer recognizes, and the one in between is the assembly language code. All right, and with assembly language code, we have a much clearer idea on what is actually happening at the processor level. Okay, so let's have an example, okay, by walking through this C and looking at it from the assembly perspective. So here in C, what we have is we have written a simple for loop. Okay, so this simple for loop has a variable, two variables, I and result. Okay, and we are running this loop 10 times, and each time we are basically going to take the value of I, add the result, put it back into result. If I were to translate this into a sequence of steps, okay, you can say that what I need to do is I take the result plus I, increment I, and as long as I is less than 10, I repeat. So you can think of this as a sort of pseudo assembly code. Okay, pseudo assembly code. Okay, that means you are now breaking up your higher level code into step-by-step instructions. Okay, your processor, okay, in general, you must think of it as something that does or performs actions in a very sequential step-by-step process. Okay, so and each step is very specific. Okay, it's very specific. That means you say you want to take this variable from this memory location. You want to add. Okay, you want to store back into a memory, store back into a register. So it's very specific. All right. So you need to think of the processor as executing instructions in a very systematic step-by-step process. So the assembly language is also written in that manner. Okay. So when a processor or any computer-based system, okay, these are the three major components. Okay, you have your processor, okay, which is basically in charge of performing all the computations. And then you have memory. Okay, and memory, the various forms of it. Okay, and you can say generally is to store code and store data. If you go later on, we will talk about fixed storage, with permanent storage and temporary storage, your ROM or flash versus your RAM. Okay, and to interconnect all these components and other subsystems, you have what you call a few different types of buses. So you have address bus, data bus, control bus, and so on. And these buses are basically a collection of wires that interconnect your processor to these subsystems. Okay, and of course, this is just a very high level view. You still have input output devices and some other peripherals that are not shown here. Now let's look at it from a perspective of what is happening, okay, with this pseudo code that we have. So just now we saw 3 lines of code. Okay, result equals to result plus I equals I plus 1, and I less than 10, then I repeat back to a earlier instruction. Okay, so you can imagine that each of these instructions is going to occupy some memory. All right, so now you think of it as each instruction occupying one block of memory, okay, or one line of memory. So the processor, okay, is always going through these 3 main actions, okay, which we call the FDE, okay, fetch, decode, and execute. Okay, your processor is always doing this. Okay, fetch can have 2 parts to it. You fetch instruction, you fetch data. Then once you have everything inside the processor, you decode the instructions, you analyze the data, and finally when everything is in place, you execute. Okay, after you execute, you get a result, and when you complete that result, you then decide what to do next. Okay, so let's look at it first, step by step. Okay, so now assuming that I'm executing these 3 lines of code, correct? So the first thing that your processor will do is take this first instruction and bring it inside my processor. Okay, because the instructions are in the memory. Okay, but the processor needs to fetch these instructions and bring them into the memory, into the processor space, and then it can start to execute. Okay, so I take this instruction, okay, into the processor. So when I take this instruction into the processor, I realize that this instruction is actually relating to some memory elements. Correct? It's relating to some memory elements. So this result and I are also variables that we have declared. All right, like how we did a C program, integer I or character I, integer result, and so on. So you have declared these variables somewhere in your code. So that means they're going to occupy some memory space. Okay, so that is this portion here. So this information, this data that is inside these memory locations also needs to be fetched, okay, and brought into the processor. Okay, so that is the first part. Okay, now after I fetch in the result, I fetch in the instruction, and I fetch in this data, okay, the result data and the I data. Okay, I now need to transfer this information into what we call internal storage. Okay, because previously result and I, these are inside the memory. Okay, but for your processor to execute the code, okay, it needs this data to be stored internally within the processor. And how the processor does it is it uses what we call internal registers. Okay, so every processor has internal registers. Different processor architectures may call it or have different naming conventions. Okay, as long as you know which processor you're dealing with and how it is named in your processor, that you know how to use it. Okay, so in this case, we will take it that we have a bunch of registers. We will call it R0, R1, and so on. and the instruction that we fetch from memory is also going to be stored inside the processor in some space. Okay, and why we want to keep this information inside the processor space is because memory access is actually very slow. In fact, that is for many years has been the bottleneck of the entire computing system. Correct? Because the processors can run very, very fast. Okay, very, very fast at gigahertz range. Correct? But your memory is still lagging behind. Okay, so that is the bottleneck, and it is still trying to catch up. Okay, it's still trying to catch up. Of course, in the later part of this module, we will talk about cache and understand how cache works, and that helps us to improve the throughput to quite an extent, but there are still a lot of areas for improvement. Okay, so what we are going to look at is how the registers are being used. So here you can see that in order for me to use this or execute this code, prior to even executing this instruction, before I can even execute this instruction, I need to first make sure that the data from result and the data from I have already been transferred from the memory to my internal registers. Okay, so this is in my memory. I need to transfer them to my internal registers first. Then when I fetch this instruction to say do the addition, the data is already there. Okay, the data is already there. Okay, so these are the additional assembly language instructions that will be generated, okay, by the compiler when you compile a high level code like C. Okay, so in your C, when you write your statement, you do not think about this, correct? You do not think about where my variable is stored, whether I need to move it around, okay, and when do I execute and so on, okay? You just write based on the logic, the functionality. But when you click on compile and the compiler comes in, it now needs to relate and also translate this C code into assembly language code. So when it does this translation, it will now have to look at, okay, I have this information in memory and I have instructions that deal with this data in memory. So when I want to execute this instruction, this data must already be fetched from memory and transferred to my internal registers. Then I can execute the instruction. Okay, so that is what these two instructions are doing. So I'm doing a load. Okay, so load is a general term used to move data. Okay, so whenever you see the term load, it means move data from memory to register. Okay, so whenever we see load this register, that means we are transferring data from the memory to the internal register. Okay, so when I execute the first instruction, R0 load I, that means take the value of I in the memory, take that data and put it into my R0 register. So that is what is going to happen. Okay, I'm going to take the data from I, okay, which is in memory, and transfer it into my R0 register. Okay. Okay, so here is what I mentioned just now, the load, okay, memory from memory to register. The other term is store. Okay, store is when you want to move it back. Okay, from your internal register, you want to transfer it to your memory. Okay, so that is the first instruction, and then your next instruction is to load the result, the variable result in your memory into your internal register R1. Okay, so that is what is happening here. Okay, so after you do that, that means you have already loaded the necessary variables into a register, and now you can do the addition. So you can see that previously, if you go back to the previous slide here, Okay, until then, okay, until this was completed, your perception of the code in the memory is still based on the variable name, correct? We are still talking about it in terms of result and I, because that is how we have written the code. Okay, but as far as the processor is concerned, it will only deal with performing arithmetic or logical operations with data in the registers. Okay, so before any operation can be done, I need to move data from my memory to my register. So since I already have these two lines of code over here that have moved this data from memory to my register, subsequently all my instructions only need to deal with register. Okay, so I don't need to talk about the memory anymore because I already transferred the data. So right now you can see that my instruction is only referencing registers. And this is good because when everything is within the processor, it is very fast. Okay, the memory is always the bottleneck. So reading from memory, writing back to memory is always very slow. But once I have that data inside my processor, inside my register, it is very fast. Okay, so all my arithmetic operation, my logical operation can be done very fast now. Okay, so now we're going to execute the additional operation. So this addition operation is the instruction. And now that I already have all my data within the registers, I can straight away use my ALU. So ALU will be looking at it in more detail. That stands for arithmetic, okay, and logical unit. The arithmetic and logical unit. So that is the unit within the processor that is in charge of all the addition, subtraction, multiplication, division, your logical operation, your AND, or not, all this stuff. Okay, so we will be looking at it in more detail later on. But for now, we are using this ALU block as the way to perform the addition operation. Okay, and once I take the addition operation, in this case, you can see that I write back to R1. Okay, because now R1 is what? If let me go back here. R1 is actually my result. Okay, result is actually R1. And what am I supposed to do? I'm supposed to take it and uh, take the result, add with I, and put it back in the result. So as far as now, as far as we are concerned in terms of the register, I take R1 plus R0, put back into R1. Okay, so you can see that the processor, the compiler, what it will do is it will translate it into code such that you transfer the necessary data to the registers, perform all the instructions and execute everything with the internal registers, and only when everything is complete in the last stage I move it back. Okay, so you try to minimize the moving of data to and fro the memory because that is very slow. Okay, so you take the data in, perform everything you need to do, then you finally write it back. Okay, so that is what we are seeing here. I'm going to perform the arithmetic operation, take the result, store it back in my register. Okay, and once it is done, I again do the increment, R0 equals R0 plus 1, and then I will check that it is not yet complete in terms of the check for the if R0 less than 10. So I do a repeat and then I go again. Okay, so effectively I'll keep repeating again and again. Okay, uh, so these instructions we will look at it in more detail later on, but eventually what will happen? Okay, so this whole thing is repeating until I reach the final iteration. When this condition is no longer satisfied, when this condition is no longer satisfied, then I will jump to then I'll go to the next instruction. And in the next instruction, basically, I already finished the loop. All right, if you look at the C code was just to do the whole addition. And if I have already completed the addition, then the computational part is done. Then I can do the last step, which is to store it back into R0. Sorry, store R0 back into I. And store R1 back into result. Okay, so there's one more arrow here, which is to store R1 to the result. Okay, so that is what is mentioned here. Okay, so the sequence is always the same. You take from memory, put into registers. All instructions are dealing with registers. Once everything is done, you transfer back. Okay, so if you look back at the code, this section is what you can relate to, because all right, when you click on the compile button, these are the things that are done to make sure that everything happens smoothly in the background. Okay, in terms of taking the data, finishing up everything and moving it back. Okay, so that is the whole idea of what is happening when you have a piece of code and you're trying to execute that piece of code. Okay, and this is also basically what we call the load store model. That means you load from memory to internal registers, you perform all the necessary work, and then you write back, okay, after everything is done. Okay, so now let's look at registers. So as what I mentioned, registers are basically small storage spaces within the processor. And since they are within the processor, they are very, very fast, okay, in terms of accessing that information. The size of these registers very much depends on the architecture of the system. Okay, so if your processor, you say it's an 8-bit processor, then your registers will also be 8-bit. Okay, you may have registers that are bigger in size to cater to different types of data formats. Okay, but if your processor itself is 8 bits, then you can say that most of your registers will be 8-bit. If your processor is 32-bit, then most of the registers will be 32-bit. Okay, now the important thing to understand is registers do not have any data type. That means registers do not differentiate to say that I'm storing character, I'm storing a float, I'm storing a real number with decimal values. No, it does not interpret any data type. Okay, the data type is something that we declare in our C code. Okay, but the declaration of the data type, whether it's positive, is a negative, and so on, those kind of things will actually play a part later on when we understand how we do the computation part. All right, so the interpretation will come in later on when we are looking at the actual computation, but the register itself will just treat it as a storage space, storing ones and zeros, that's all. Okay, in the MIPS processor that we are studying in this module, there are 32 registers. The 32 registers can be referenced through numbers, okay, 0 to 31. They can also be referenced by name. That means they have specific names for different types of registers. Okay, so later on we will look at some of the assembly language code, and then you slowly get used to it. Okay, so assembly language is very tedious. Okay, and it takes some getting used to. Okay, but once you are a bit familiar, you will find that it's a bit manageable. Okay, after some practice. So in terms of the numbers, okay, you can reference them with the numbers. So as you can see here, it's from 0 all the way to 31. If you prefer to use the name, you can also use the names. Okay, in some examples, we will use both numbers and names. Okay, some of them are reserved, okay, for specific purposes. Like for example here, 28 to 31, these are reserved for the different users in terms of stack pointer, global pointer, and so on. You also have a 0 register, and this 0 register actually stores a value of 0. Okay, and it is actually a very useful register because in many cases using this 0 register can help perform some of the actions quite easily, which we will see in a while. And yeah, so this is just an overview. We will be looking at some of these registers and their use cases along the way. Okay, we look at the examples. Okay, so let's look at this uh, assembly language instruction. Okay, for assembly language instruction, okay, like I said, it is very specific, focus on fulfilling a particular objective. Okay, in C program, you can write a very complex statement, correct? You can write z is equals to 2 plus x, multiplied by y, then this whole thing divided by z, divided by a, something like that. Okay, so you can write a very complex statement in C. But as far as assembly language is concerned, everything is very systematic, step by step. So if you were to write this in C, it will translate to many assembly language instructions, breaking up this instruction into the individual steps. Okay, so in assembly, everything is very focused. Every line of code is very focused to fulfill a particular objective. Okay, and each line contains at most one instruction. Okay, so in C, you can do multiply, divide, plus everything in one line, correct? But as far as assembly is concerned, every line, every instruction is very specific. You doing an addition, doing a subtraction, doing a shift, and so on. To add comments, you can use the hex sign. By putting a hex sign, and then anything after that is a comment. Okay, so similar to your double slash in C. Okay, so let's look at the general instruction syntax. So there are different types of instruction formats. Okay, so the different instruction formats will relate to different ways of writing these instructions. What we're looking at is what we call the R-type instruction. Okay, so this is what we call R-type. We'll be learning of different types along the way. In an R-type instruction, basically what we are saying is R-type stands for register type. Okay, and in R-type instruction, your source registers, your source of your data, and your destination of your data are all registers. Okay, are all registers. That's why we call it R-type instruction. So for this R-type instruction, you specify 3 registers, and the format is such that the first word that you write is what we call the operation. What do you want to do? Add, shift, subtract, and so on. Okay, or and or something. So you write the operation, and then the first register that you specify here is actually the destination. Okay, so it's operation followed by destination, then source 1 and source 2. Okay, so that is the instruction syntax for R-type instruction. Okay, operation, destination, source 1, source 2. So in this instruction, what am I doing? I'm taking the data in register S1. I'm taking the data in register S2. I'm going to add them together, and I'm going to put the result in register S0. Okay, so that is what I am intending to do with this instruction here. Okay, so like as you can see, it's very specific. 2 data, 1 operation, and the result I saw somewhere. Okay, so that is the objective. Okay, as you can see here. So let's look at a few more examples. Now in C, when you write a statement like this, A equals to B plus C, we are basically taking 2 variables, okay, and we are adding them, putting the result in another variable. As what we saw earlier, your MIPS processor does not do arithmetic operations on memory. In order for me to do arithmetic or any form of ALU based operation, the content of the memory has to be first shifted into my internal register. Okay, so there has to be a mapping. Okay, something that happens. So this mapping is done by the compiler. Okay, when we are doing it at a high level. When you are writing the code yourself, then you need to do your own mapping. Okay, so you need to specify which register is actually holding my information. Okay, so in this case, what we have shown you is that the mapping is already done earlier on. Okay, so before I can execute the code, I need to do the mapping. Okay, that means I need to say this is B, this is C, this is my A. Okay, the mapping here, this mapping of variable to register is arbitrary. Okay, when you are writing your own code, you are free to choose any register you like. Okay, so there is no specific mapping. Okay, similarly, when the compiler does it, it has its own mapping rules that it may follow, but that doesn't concern us. Okay, for our module, we just need to know if a mapping is given. If there is no mapping is given, you are free to use any of the registers. Okay, so if I go back to this earlier slide here on the registers. Okay, so in most cases, the registers we will use this A0 to A3, T0, T7, and T8 to T9. Okay, so these are the registers that we will use quite often, okay, to do all these mapping. Okay, so if there is no mapping given to you, you are free to use any mapping you like. Okay, now subtraction. So for addition, there is no difference between S1 and S2, correct? If C was here or B was there, doesn't matter. Either way, it will still be the same. Okay, but for subtraction, the order matters because you need to make sure you understand which variable is subtracting the other variable. Okay, so in this case, I need to make sure that B is mapped to S1, C is mapped to S2, and then the result is in A. Okay, so that is important for subtraction. Okay, so this is like what we mentioned just now, a complex statement in C. Okay, why is it a complex statement? Because it involves 3 variables and 2 operations. Okay, your processor is only going to handle one operation at a time. Okay. So this is considered a complex operation. So in order for us to do this complex operation, we actually have to break up this statement into multiple assembly language statements. Okay, so what will happen is okay, you need to translate this into 2 or more assembly language statements. So in the first statement, you can perform the addition first, all right, and then after that you can do the subtraction. Okay, so here we are just randomly allocating that B is over here in S1, C is in S2, and that result is now stored in another register called T0. So T0 is just temporarily storing this information because later on I will use T0 to do the subtraction with S3, and S3 is now D. Okay, and finally I get the result S0. S0 is my A. Okay, so this is again to show you how a C statement like this might get translated into assembly. Okay, another example, again another complex expression, 2 addition, 1 subtraction, and 4 variables. Okay, and we have given you the variable mappings. And what you need to do is you need to break it up into multiple instructions. So I may do this as one operation, do this as another operation, and then finally do the subtraction. Okay, so when I do intermediate steps, I also need temporary registers to hold this answer for me. Correct? So G plus H, I need to store it somewhere. I plus J, I need to store it somewhere. And then finally, I can do the subtraction. Okay, so that is what is shown here. So G plus H, I store inside T0. Then I plus J, I store inside T1. And then finally, I do the subtraction and the answer goes into S0 over here. Okay, so these are again more examples, okay, that you can see. Okay, so the whole idea that we're trying to show you here is whatever you do in C is of course a lot easier because you can write one full mathematical expression there. But when you translate to assembly, you still have to break it up into procedural step-by-step instructions. Okay, and if you're doing it on your own, then you need to decide how you're going to go through and organize your assembly language code. Okay, so until now, what we saw is what we call the R-type instructions, okay, where both the source is registers, I mean the source of the data are registers, and the destination also a register. Now we're moving on to another type of instruction called the I-type instruction. So in I-type instructions, the I stands for immediate. Okay, so in my code, I will specify a register and I will also be able to specify an immediate value. Okay, that means a constant value inside my code. So similar to how in C you may write A equals to A plus 4. So this 4 is a constant, correct? You are always going to add 4. Okay, so in translation to MIPS, okay, I can put the instruction with S0 being the register A and 4 being the immediate, and the destination is also A. Okay, and what has changed? The instruction has now changed. Previously was add, now is add I. Okay, so these are the variations of the instruction. So the add operation by itself, okay, if you go back here, is just R type. Okay, if I just say add, it is R type. But the moment I say add I, it is add immediate. Okay, so source 1 is a register, source 2 is a constant. Now, this constant value, again, there is a limitation to how big it is, and that is basically minus 2 to the power of 15 to 2 to the power of 15 minus 1. And if you look back to our complement, 2's complement notation, this translates to having a 16-bit value, 16-bit 2's complement representation. Okay, so the immediate value that I can specify is actually a 16-bit 2's complement number. Okay, why is it 16-bit? Okay, we will see later when we are looking at the processor. Okay, so you can't do a R type with a constant. Okay, that means if you were to type an instruction that says add, okay, S0 with 4, this is basically a syntax error, correct? Because if you say add, all must be registers. If you put a immediate, this will be add I. So it's just like writing C. Okay, if in your C you forget a semicolon, it will say it's a compile error. All right. If in your C you say 4 is equals to 8, you will say compile error. All right, because these are not allowed. Something is wrong. So similarly, if you were to write something like this in your code, okay, and you try to assemble the code, okay, you will flag out as an error because this is an invalid instructions. Okay, if you say add, it has to be all 3 registers. Add I, then one of it can be a immediate. Okay, so in the lab exercise, okay, so if you swap around, it also will flag out as an error. So the order is important. Okay, that means if I use add I instruction, it has to be destination. Okay, it has to be destination. So whenever I use add I, it has to be destination. Okay, followed by source one, followed by immediate. Okay, this ordering is fixed. You can't change it. Okay, both sources as constants is not supported. Okay, so there are only the certain type of uh, instructions that are supported. We will look at that when we are reviewing the instruction set of the processor. Okay, so that is why we said earlier that this is actually uh, uh, the ISA is important, the instruction set architecture. So the instruction set architecture will actually give us the uh, full breakdown of the type of instructions that are supported by the processor. Okay, so definitely whatever code that you write in C, as long as it is a valid C code, it will be able to compile and run successfully on the processor. Correct. Now, how it translates to it, how it sort of converts your C to assembly, the compiler is definitely smart enough to do that. So no matter how you write your code, how many constants you have, how many variables you have, doesn't matter. It will know how to move around and play with the instructions to get it to work. Okay, so along the way, when we look at all the instructions that are supported by the MIPS hardware, you will see how some of this works. Okay, how some of these things that may seem, okay, how do I do this? How do I do that? Okay, you will see that the tricks that the compiler is actually doing, okay, to make it happen. Okay, so as now I mentioned there is a zero register, and the zero register actually has a value of 0 inside it. Okay, and why is that useful? Okay, so in a statement like this, f equals to g. So in C, we know that we are taking the value of g and copying it to f. Okay, but there is no copy instruction in MIPS. Okay, so every processor has its own set of instructions that it supports. Okay, and what we need to do is we need to figure out, okay, we need to figure out how to uh, play around with what we have to achieve our objective. Okay, so again, why some may be supported, some may not be supported, and so on. There could be many reasons, historical, when it was designed, for which or what purpose this processor architecture was designed. So there could be many reasons, background information on it. Okay, but for now, what we will look at is, okay, when we take this processor, this is what we have. How do we use this to create the code we want? Okay, so that is the thinking we must have. So for MIPS, we do not have any direct assignment instruction or copy instruction. So what we do is we can do an addition with a 0, because S1, okay, S1 plus 0 will come back to S1, and then I can assign to S0. So this is equivalent to saying that S0 is assigned whatever S1 has. Okay, so the same idea of copy, but since there is no copy, you can actually do this add with 0. Okay, at the same time, what MIPS has done is they have also given you these pseudo instructions. Pseudo instructions are instructions that you can write in your assembly language code, but it actually doesn't get translated as the way you write it, because it's just a wrapper to make the code look more readable and more easy to comprehend, but it will actually translate to the pure MIPS. Okay, so when you write something like this, move S0, S0, S1, it becomes quite clear. All right, that means I'm trying to do a copy of S1 to S0. Okay, so in terms of a pseudo instruction, it is more readable. But when I compile this code, it will still translate to something like this. It means a pure MIPS instruction where this same operation is carried out, but we be using one or more type of instructions. Okay, so in this case, move you can say can be replaced by a single add with zero instruction. There are other pseudo instructions that will translate to a few MIPS assembly language instructions. Okay, so again, that is to give some convenience to the programmer, okay, to use some of this sort of shortcut uh, code to speed up your coding and make it more readable. Okay, so we will just touch a bit on logical operations, okay, and then we will end it for today. Okay, so for logical operations, okay, okay, so what we saw just now are some basic arithmetic operations. For logical operations is your AND, your OR, NOT, and so on. And logical operations view the entire 32 bits as a single, as just 32 bits. Like I said, whatever is on register is not interpreted as any data type. Okay, it is just that bits, raw bits as you see it. Okay. In terms of logical operations, these are the common operators in C that or in Java that you will actually use in MIPS. Shift left logical, shift right logical, and immediate, or immediate, and NOR. Okay, so we will see how to do this. Okay, so let's just quickly review logical operations. So logical operations for AND, as long as I AND with a 0, the output is a 0. Or if I OR with a 1, okay, the output is a 1. Okay, here anything, as long as there is a 0 anywhere, the output is always a 0. Only when everything is a 1, the output is a 1. Okay, NOR is the opposite of OR. Okay, so NOR is basically not of OR. Okay, so whatever the OR truth table is, the opposite is what you get for NOR. For exclusive OR, basically the easiest way to remember this is if bits are different. Then output is a 1. Okay, so as you can see over here, A and B. So 0, 1 is 1 and 1, 0 is 1 because the two inputs A and B are different. Okay, if they are the same, then the output is a 0. So that is one easy way of remembering XOR. Okay, so let's look at this shift left logical. So what is shift left logical? So when you say shift left, okay, so shift left is equivalent to multiply by 2 power, correct? Every time you shift left by 1, okay, it is equivalent to multiply by 2. Shift right by 1 is equivalent to divide by 2. Okay, you would have probably seen this or used this before. And this is of course a very useful technique, okay, because multiply and divide operations are what we call very compute intensive operations. Okay, that means at the processor level they take a lot of clock cycles. Okay, so that is why when if you write code that involves a lot of multiplication, a lot of division, and you need to use the multiply blocks in your processor, they may take longer time, okay, compared to just using arithmetic or shifting operations. So in this example, okay, if I say shift left logical, basically I shift left by a certain number of bits and the empty positions are filled with zeros. So if this is my original S0, and I take S0, shift left by 4. So if I shift left by 4, what happens? Okay, this first 4 bits will get shifted out. So this one comes here, this one comes here, and so on. And this one comes here. And what comes in 4 zeros. Okay, so that is what is happening here. Okay, so the 4 zeros come in over here, and this first 4 bits have been shifted out. That means they're no longer there. Okay, shift right logical, again, similar thing. You shift to the right and fill the empty position with 0. Okay, and so again, these are some of the smart things that your compiler will try to do. All right, so whenever it sees that you are going to do a multiplication or division by a number, it will try to see if it can replace that multiplication with a shift operation. Okay, so writing a C statement like this, a equals a times 8, will actually translate to a shift operation in the assembly language. Okay, because the compiler will be smart enough to know that this is a more efficient operation to carry out. Okay, so you'll do a shift left by 3. Okay, in terms of bitwise operation, you can use this to do what we call masking. Just let me check where I am. Okay, so let me just finish the AND and the OR, and then we'll end it here. Okay, so the masking operation, okay, is a very useful technique. Okay, you would have or might have used masking techniques in C before. Okay, so in masking, what we want to do is we only want to focus on certain bits in a multi-bit data. Okay, so in this case, you have T1, which is having the full 32 bits here. Okay, but I'm only interested in these bits. Okay, this is 10 to 13. Okay, bit 13 down to 10. So these are the bits I'm interested in. All right, and I do not want to worry about the rest of the bits. So what I can do is I do a mask, and when I do a mask, okay, when I do an AND with a 0, everything else, anything that I end with a 0 will automatically become 0. Okay, and the bits that I want to keep, I end with a 1. Okay, so those bits that I want to keep, I end with a 1. Those original bits will be retained in the result. So this is one way of using a mask to decide or focus on specific bits in your register. All right, so in this case, if I'm only interested in the last 12 bits, I just need to make sure in my mask I set the last 12 bits to 1, and everything else become 0. All right, so this AND can be done, and the final result is stored here in T0. Okay, there is also the AND I version of AND instruction. That means you can also do an AND with the immediate. Okay, so over here, instead of doing this AND with register and register, I can also do with immediate. Okay, so the OR operation is basically to place a 1. Okay, so the OR operation is useful to place a 1 in any particular position, because when I do a OR, okay, with 1, the final result for those bits will always be 1. Okay, so the whole idea of masking is you are able to specifically change certain bits without affecting the other bits. Okay, so that is the main idea of using the AND and OR operators in your logical operations for masking. Okay, so I think we can end here. Okay, there is no need to rush to finish the slides, because the next set of slides are also going to follow up. Okay, so in this set of slides, okay, and the next set as well, basically we are reviewing assembly language programming. Okay, and we are also looking at beginning to understand a bit about how the processor works. Okay. Once we are done with assembly language programming, we will look further into how we can translate this assembly language into the machine code. That means the ones and zeros. And then we will look at how these ones and zeros are actually interpreted by the processor. Okay, that means when we say add S0, S1, S2, okay, how does this translate to ones and zeros? And when these ones and zeros are fed into the processor, how does it know and sort of interpret these ones and zeros to perform the right action in terms of the add operation, taking the data from the correct registers, writing the result into the correct register, and so on. Okay, so those are the things that we'll be looking at once we have completed the assembly language part. All right, so as mentioned, it's going to be a bit heavy, okay, in terms of the content and the things we are covering. All right, and it's building up. Okay, they're all building up. So you have to make sure that you understand everything along the way, so that when we move along, you are able to keep up. Okay, any questions, anything that you have, you're not sure, feel free to email me, okay, or WhatsApp me, and you can just discuss what are your doubts. All right, I just want to make sure everybody is catching up. All right, and you don't get lag behind too much. Okay, that will be difficult for you to catch up. All right, so that's all I have. Okay, thank you very much. Okay, and I will see you all next week. As mentioned, I will upload the videos for this week plus any other additional videos, and I'll send you all the link. All right, so thank you everybody. Good night. Okay, I'll see you all next week.